Okay, diffraction gratings. A diffraction grating is a large number of small openings that essentially acts like, instead of a double slit like we would have had in Young's experiment, many slits that create a very similar interference pattern. So with the double slit experiment, we had two openings and we had two light sources coming together to form an interference pattern. With the diffraction grating, we have many openings coming together to form an interference pattern. The interference pattern from a diffraction grating shows the same basic formula as the one that we get from a double slit, where instead of the distance being the distance between just two openings, the distance here is the distance between each successive opening. The interference pattern is very similar, but it's not exactly the same. It's actually a little bit better to work with. The dark spots are darker and the bright spots are brighter, and that works out pretty well in terms of making the interference pattern a little bit easier to work with and a little bit easier to see. Typically, with these patterns, we're not given the distance between adjacent slits, but instead we're given a distance. Let's say the diffraction grating will be 1 centimeter wide, and then we're told how many openings there are in that 1 centimeter. So a typical value might be 500 openings in 1 centimeter. We can then figure out that the distance between the individual openings must be 0.002 centimeters, or 2 times 10 to the negative 5 meters. So with these diffraction gratings, we get a nicer interference pattern. It's easier to work with for experiments, but in terms of the actual mathematics or the calculations we can do with them, they're the same. We just have this extra step where we have to find D. So a diffraction grating with 300 lines per centimeter is being used to show the interference of red light 630 nanometer. If the interference pattern is incident on a screen that's 1.2 meters away, determine the distance between the bright spots. So D, 300 lines in each centimeter. So 1 centimeter divided by 300 lines will give me the distance in between the individual ones. So 0.01 divided by 300. So this is going to be 0.033 centimeters, or, 1 divided by 300. Sorry, I'm messing that up. 0.0033, that just keeps going, centimeters, or 3.33 times 10 to the negative 5 meters. I have an L, 1.2 meters, and I have my wavelength of light, which is 630 nanometers, 630 nanometers. So delta X equals lambda L over D. So 630 times 10 to the negative 9 meters times a length of 1.2 meters divided by the distance in between my slits, which is 3.33 times 10 to the negative 5 meters. And all this works out to be 2.27 centimeters. Or it actually gave me 0.0227 meters. So diffraction gratings are useful. The mathematics for deriving the relationship of where the bright spots are is essentially the exact same as it was for a double slit. We just assume that we have lots and lots of double slits that are right next to each other. Using that, we get an even better, clearly defined interference pattern where the bright spots are very bright and the dark spots aren't bright at all. They're completely dark. Useful for experiments because it makes the interference pattern a little easier to see and a little easier to measure. Just a little trick here where we have this new equation, or this new way of finding the distance between the slits, by dividing the width of the diffraction grating by the number of holes that would be in it. So that's how you can predict the interference pattern for a diffraction grating.